Today we will be looking at the 2025 Putnam A2 problem, where we want to find the largest real number A and smallest real number A, or smallest real number B, such that sine of x is completely bounded by the quadratics ax times pi minus x and bx times pi minus x for all x in the interval 0 to pi. And so to give a little bit more intuition as to what this looks like, it's nice to draw out a little bit. So from 0 to pi, we have that sine x looks something like this, where it achieves its maximum at 1. Ax times pi minus x completely lower bounds it. The quadratic looks something like that. And bx times pi minus x completely upper bounds it. So the quadratic would look something like that. I want to find the largest a and smallest b that is able to do this. But from this drawing, we can sort of guess, if it wasn't clear before, or from looking at this immediately, that this graph looks symmetric across pi over 2, and it indeed is, because sine of x is symmetric across pi over 2, and then both quadratics, when written in this form, we can see that it's symmetric because by plugging in u is equal to pi minus x, we will get the same values by plugging in x and u, defined this way for all x in the interval. So we indeed have that the entire expression is symmetric across pi over 2. So we can reduce the interval that we're looking at to just 0 to pi over 2. Yeah, so now we want to find a and b. And so it'd be nice if we could isolate a and b in this expression so that they're easier to analyze or find. And we can, right? Because both a and b are divided by x times pi minus x. So we can immediately just divide by that and get that a is less than or equal to sine of x times x, sine of x over x times pi minus x, which is less than or equal to b. And note that x times pi minus x is non-negative on this interval 0 to pi over 2, so we don't have to flip any inequality signs. But I say non-negative because at 0 the denominator becomes 0, right? And that is an issue. So we can really only look at this function on the interval from 0 to pi over 2. And so now written in this form, we see that we just need to find the minimum and maximum value of sine x over x times pi minus x on this interval. And it's not immediately clear how we can do that, but one nice way to analyze such functions is to look at their derivative and see if there's any nice properties of how the derivative behaves, so we can see when the function is increasing or decreasing, and then try to go from there. So if we let f of x be equal to sine of x over x over pi minus x, we have that f prime of x is equal to sine of x, or sorry, cosine of x times x pi minus x minus sine of x times pi minus 2x all over, so what is this here? All over x times pi minus x all squared. And right, we want to see when this function is increasing or decreasing, so we really only care about the sign of its derivative and not really its magnitude. So the denominator of f prime is always positive since it's squared. So we really only have to look at its numerator. So let's let g of x be this numerator, right? Just copy this over. We have g of x is equal to this whole expression. And so what does this tell us about the sign of f prime? Again, it's pretty hard to see, or there's not really a clear way to go, but we can try to see how it behaves at its endpoints, right? 0 and pi over 2. At 0, we have that g of 0 is, this first expression is 0 because it's an x, and sine of x is equal to 0. So at g of 0, we have that, at x is equal to 0, we have that g of 0 is 0. And then at pi over 2, we have that cosine of pi over 2 is 0, and then pi minus 2x is 0. So this expression is also equal to 0. Yeah, so we have that at both its endpoints, the numerator is equal to 0. And so a sort of very like greedy idea is to sort of wishfully think that maybe g is completely positive on this interval, right? So if g is completely positive on this interval, or at least non-negative, then we have that f is always increasing, or f prime is also always positive on this interval. And so f is always increasing. So we have that the minimum of f is at the limit as we approach 0, and the maximum of f is just at pi over 2. So if we can conclude that, that would be very nice to solve our problem. And so how do we sort of determine if g is completely positive or non-negative on this interval? Well, we look at its derivative again, right? And see how it behaves from there. So we then have that g prime of x is equal to negative sine of x times pi minus x plus cosine of x times pi minus 2x minus cosine of x times pi minus 2x plus sine of x times negative 2, or I guess it should be jumped ahead a little bit. Minus sine over x times negative 2. So expanding this, hopefully some things will cancel out. So we have that negative pi x sine x minus, or plus, sorry, x squared sine x plus pi cosine x minus 2x cosine x minus pi cosine x plus 2x cosine x, and then plus 2 sine x. And we do see that some terms cancel out. We have a positive pi cosine x here and a negative pi cosine x here. We have a negative 2x cosine x here and a positive 2 cosine x here. So we're really just left with sine of x times x squared minus pi x plus 2. And okay, so that simplified pretty nicely. And so again, we want to look at how g behaves. So looking at g prime, we again only really care about the sign. And from 0 to pi over 2, sine of x is always positive or non-negative, so we can ignore that. And so we really only have to analyze x squared minus pi x plus 2 now. And right, so it will look something like this. So we'd like to find where these two roots are. And so by the quadratic equation, we have that x is equal to pi plus or minus pi squared minus 8 over 2. And so sort of approximating this, we have 3.14 plus pi squared is going to be like 9.1 or 2 something, minus 8, that's 1.1 something, and square rooted, that's still like 1.1 something, so that's very small, over 2. And so if it's plus, we have that 3.14 plus 1 point something small is 4 point something relatively small, so divided by 2, we have one root is 2 point something, and the other root is 3.14 minus 1 point something small, that's going to be like 2 point something small, so we have 1 point something small. And so we see that in particular this root is in the interval that we're looking at, right? 0 to pi over 2. Because pi over 2 is like 1.5 something, and that should be, we can be pretty sure that's greater than 1 point something small. So in our sort of model here, or graph here, we have 0 to, let's call this pi over 2. So we have that from 0 to, let's call this root r, right? From 0 to r, we have that it's positive, and then from r to pi over 2, we have that it's negative. Or g prime is positive from 0 to r, and g prime is negative from r to pi over 2. So that means g is increasing from 0 to r, and then decreases from r to pi over 2. So let's see what that sort of looks like. Again, I'm drawing it out. We have 0, pi over 2. Right, we knew that g of 0 and g of pi over 2 are both 0. Right, so we start here. It increases for some time. Let's say to r, let's say r is here. Increases until r, and then decreases until r. So we sort of want to, intuitively it feels like this is what g should look like, right? It goes up in some weird way and then comes down in some weird way. But in particular, it means that g wants to always be positive on this interval, because let's say it dipped negative somewhere, right? So we have g increase some, we hit r, it decreases to something negative. But we know that r to pi over 2 always decreases, so we can never increase back to pi over 2, which is 0, right? And because g is continuous on this interval, because sine x and x times pi minus x are both continuous, so g is continuous, so we can't really jump up to pi over 2. So we can never have that g is negative on this interval. So that means on 0 to pi over 2, g of x is strictly greater than or equal to 0. And that's exactly what we were looking for, right? If g of x is always greater than or equal to 0 on this interval, then f prime is always greater than or equal to on this interval. So f is always increasing on our interval. So we indeed have that f has a minimum at the limit as x approaches 0, where its minimum and maximum are at its endpoints. And since it's increasing always, we have that its minimum at its limit as x approaches 0 of f, and max at just f at pi over 2, right? So now it's just an issue of finding what this is. So I guess the easier one is finding the max at pi over 2. Let's copy f down here again. So at pi over 2, we have that f of pi over 2 is sine of pi over 2 times pi over 2 times pi minus pi over 2. So this is 1 over pi squared over 4. So which is just 4 over pi squared. And so this is what b is. And this, yeah, that's equal to b, that's its upper bound. And then its minimum is its limit as it approaches 0 of f of x is equal to limit as x approaches 0 of sine of x over x times pi minus x. And if you've taken an analysis course or a physics course, you might seen that for very small x, sine of x, we can use the fact that sine of x behaves very similar to x. So in particular, we just have that limit as x approaches 0 is equal to x over x times pi minus x. And so this immediately, the x's immediately cancel out now. So we just have the limit as x approaches 0 of pi minus x, or x approaches 0 of 1 over pi minus x, which is just 1 over pi. And that is Ra. So in the end, we have that, right, we have that the largest real number a and the smallest real number b, such that this equation is true, this inequality is always true, is when a is 1 over pi and b is 4 over pi squared.